and we will wait for 5 minutes for some students to join. And if students not join, then I will start my class to follow the timing instruction. Yes, I'm waiting now. So, hello students. Actually, for this course, we have three more people in my class. In the while uh, in the live session, even if you're not able to join some, that is a Fourier transform PMRF called it IIT Hyderabad. For this week. So the key points were the relation between real axis Fourier transform and complex plane analysis. Okay, so what exactly that forces the Fourier transform and the complex plane analysis? Okay, and the relationship between them. So we will be seeing that through Laplace transform, like transform through Laplace transform, because we often know that the frequency domain transformation is Fourier transform, but it is also limited to Laplace transform. Okay, and for some discrete time systems, we use jet transform. So, what are the differences between these transform, and what are the things that we apply for these particular things? Okay, so that is one of the reason. Like we will be showing the real focus on the complex plane analysis. And the second point that arises in our mind is like why introduce the complex frequency domain that is S is equals to sigma plus j omega. Like previously it was simple omega, okay. But we can sometimes refer that respect to j omega sometimes or omega, okay. But the complex frequency domain is something like that has sigma plus j omega, okay. And third thing is that is used in signal processing and system analysis. Okay, so from the conceptual view, the Fourier transform can be seen as a special case of the Laplace transform. Okay, so when we have the real part as zero, then that can be seen as a special case of Laplace transform. And what are the understanding of the conceptual overview is we have to understand the poles, zeros, and the reason of convergence in complex planes. Okay, that helps analyze the system behavior. So, so if we talk about the basic, the Fourier that is continuous times. We have when we talk about Fourier transform series, table in our mind. For you to understand. Okay, so I have here time and I have here as frequency domain. So when we talk about the time domain, suppose we have continuous time and a period. Second is continuous time periodic. Second, third is discrete time. A fourth is discrete time and periodic. So if we transform it to frequency transform, and this is all about the Fourier transform. This is all about the Fourier transform. So if we have continuous time and aperiodic signal in the time domain, it will transform. And what frequency transform? It will transform the frequency domain, definitely, where we have this omega. Okay. So which type of Fourier transform we will use here? So here we will use is CTFT. This is continuous time transform. When we have a continuous time and a periodic signal, then what type of Fourier transform is used? So as we know, any periodic signal can be written as a form of sum f sine and cosine. So the periodic signal will be written as a sum of cosine and sine through Fourier series. So here we will use CTFS. And plus Fourier transform. Okay, so first the periodic signal will be written in terms of sine of cosine and sine, sum of sine and cosine, using what? Using Fourier series. And after that, it will be transformed. Why it is very, very easy if you write in the term sum of sine and cosine and then transform, then the sine cosine Fourier transform that is an impulse function. So as a result that you will get is a train of impulse function. You get train of impulse function. Okay. So and third part is we kind a periodic signal in our hand. So what type of Fourier transform it is used? It will be used as DTFT, discrete time Fourier transform, and referring differences. Okay. Okay. So my concern now, if you have CT with aperiodic signal, what output here? What output you will get? That is different color. So output you will get continuous time and aperiodic signal. Okay, it is an aperiodic signal only. Okay. When we have CT and periodic, then you will get and aperiodic. When we use discrete time and aperiodic, so you will be getting continuous time and periodic. Okay, but when we have discrete, so so answer is DFT, discrete Fourier transform. It is the DTFT. Okay, so you'll be using. So you will be using DFT as this. So this is a table that you have to. Okay, so it's very, very important. You should note down this. Okay. So as we know, when sigma tends to zero, that whole Fourier transform, sorry, Laplace transform will transform to Fourier transform. So also we should know understanding of poles, zeros, and the reason of conversion in complex plane health analyzes system behavior. We will see how it analyzes system behavior. Okay. Definition and the basic properties. The Fourier transform of the continuous time, as we know, and we were discussing on the last 2-3 class of the Fourier transform infinity of t power minus a omega t dt. Okay. So sorry, my device connection goes off in between. So what I will do is I'll repeat the things. Okay. When you have the extension to S, so instead of e power minus j omega t, what you're exactly having is x of t e power minus st. Okay, where S is equals to sigma plus j omega. So the key properties are the linearity, time shifting, frequency shifting, convolution in time, which leads to multiplication in frequency domain. Okay, this we will come back again. And if you still have doubt like how to have the formulas for this, I have been telling you from the last classes, but if you have doubt, you can just let me know. I can have the uh, I can just have I can just repeat it again. That's not a problem. Okay. So for example, you have Fourier. So you have the question in your mind that find the Fourier transform of xt is equals to e power minus 2t ut, where ut is a unit step function. So as we know, we have to just put in the formula. So that formula is we just identify the function and limits of integration. We have to write down the integration function and evaluate. Okay, evaluate carefully considering the convergence. Okay. So for example, you have just keeping that in the formula x of omega is equals to, so here remember that is x of s. Here it was x of omega. Okay. So x of omega is equals to minus infinity to infinity e power minus 2 t ut e power minus j omega t dt. And since ut is 0 for t less than 0, the integral becomes x of omega is equals to 0 to infinity e power minus 2 t j omega t 0 to infinity e power minus 2 plus j omega t dt. And if you integrate, you will be having this one, and x of omega is equals to 1 upon 2 plus j omega. So what is the summary? I'm starting from the Fourier transform. I'm just leading you to how to it will go to Laplace transform. So summary and insights are like Fourier transform can be seen as an evaluating the Laplace transform on the imaginary axis. Okay, when you are evaluating the Laplace transform on the imaginary axis, like sigma is equal to 0, or the convergence requires real of s is greater than 0. In this example for the Laplace transform, but for the pure Fourier transform, it specifically take. So whenever the convergence okay, requires real of s is greater than 0. That is in this example. the Laplace transform, but for the pure Fourier transform, we specifically take sigma is equals to 0. Okay, so complex analysis tools, that is residues, pole zero plots, can greatly simplify the understanding of system behavior. Now we'll talk about the Laplace transform of xt. Okay, here e power minus st. So poles and zeros, like values of x s for which x is equals to 0 is zeros. Okay, the values of s for which x has become unbounded is poles. Like suppose s plus a divided by s plus b, you have fxs. So what do you think, which will be the poles and zero? So as the definition says, that values of s for which s is equals to 0. So xs is equals to 0, you'll keep as 0. So s plus a is equals to 0, then s is equals to minus a is the zeros. When the values of s for which x is becomes unbounded, so in that case, s x is equals to 1 by 0, suppose. Unbounded, infinity, okay. So in that case, a by s of b is equals to 1 by 0. And that case, s of b is equals to 0. So s equals to minus b is a poles. Significance is poles determine the system stability because it is giving the unbounded relationship. Suppose it is having the bounded or unbound characteristics, okay. If it is the system is behaving like this, so what will the convergence rate? So the system won't be bounded, won't be unbounded. So in that case, pole zero plots guide filter and the control systems design. Okay. So if we talk about some algebraic and graphical interpretation, so transfer function is of the form of numerator divided by denominator, and you can write that as x minus z1 s minus z2 dot divided by s minus p1 s minus p2 dot. So the roots of numerator is actually zeros and the roots of denominator is poles. So graphical point of view, the poles typically marked with the x, where this is marked with 0. So if we need to find the poles and zeros diagrams in this case, so how will it look like? So s is equals to minus 3 is 0. So let us say here minus 3. S is equal, this is sigma plus j omega. Because j omega term is 0 here, so s is equals to minus 1. So this is 0, minus 1, minus 2. I need to plot. So poles in the left half plane indicate a stable system. So we have left half. Since we have pole, sorry, so we have left half, this one. Suppose in the left half plane indicates a stable system. Zero location influences the frequency response, but not the stability directly. Okay. So whenever we are asked to find the stability, okay. So but just by seeing the pole zero diagram, we can easily find it, isn't it? Or we can easily find it. We can have this diagram, and since zero location doesn't influence the stability, but it does influence the frequency response. So knowing poles and zeros is it's crucial for control design and the filter system. Now I will tell you the concept of region of convergence. Okay. So the set of S values for which Laplace integral converges. Okay. That is a definition. So what is this definition? definition states that the set of S values, so S values was, it was there in the power of E of minus ST. Okay. Whereas it was e power minus j omega in case of Fourier transform. Okay. Now, why it is important? Because it determines the stability and the causality for systems. And it is also a function can have multiple ROC, each implying different time domain behaviors like causal, anti-causal, or two-sided. So graphically, if you want to see, you'll have a plane sigma j omega. So whatever the values, okay, that integral becomes converges, like should not diverge. So any values set, so some set of values. Okay, that is what the ROC states. So typical ROC's definitions. So please remember this in your mind because that you can directly ask the questions. So right-handed signals. Okay. Right-handed signals x of t is equal to 0 for t less than 0, for which ROC, the real of S, is greater than sigma 0, it's right-handed signals. So we are talking only of real of S. So what is the saying is if you have t less than 0, okay, so this value is 0. So this particular thing is right-handed signal. Okay. When I said we talk about, if I talk about left-handed signals, so this particular x of t is equals to 0. If t greater than 0, then ROC of real of S is greater than sigma 1. But that is the case where you exactly have left-handed signal. Okay, simple opposite of these two. If I talk about the two-sided signals, okay, so RAC may be a vertical strip from this to this. So let me plot this. The real of S is greater than sigma 0. So suppose sigma 0 is somewhat here. So real of S greater than sigma 0. This one. This is right-handed signal. Okay. Real of S less than sigma 1. So let me keep sigma 1 here somewhat here. Sigma 1 is less, so less. So this is a right-handed. This is left-handed. And suppose vertical strip. So let me take a different color. So this is, if it is lying between sigma 1 and sigma 0, provided sigma 1 is great, sorry, sigma 0 is sigma 0 is greater than sigma 1. So this is two-sided signal. Okay, so if I talk about the causality condition, causal signal, what is a causal signal? So causal signal, which is practical in nature. Okay, so practical means it doesn't depend on the future inputs. Okay, so whatever signal which depends on the past inputs. Okay, past input and the present input, then that is a causal signal. Okay. And what was the criteria to determine the causal signal if we have the impulse response? That is ST. What was the criteria? ST is equals to 0 for t less than 0. That was the criteria. ST is equals to 0 for t less than 0. Okay. I hope that you remember. So for causal signal, if the XT is or the HT, any signal is causal, okay, the ROC extend to real of S, okay, to plus infinity. So ROC extend to real of S to plus infinity. So example value, let us say. So if we have why it is leading to plus infinity, first of all, because as we know the previous, like whatever the value for t less than 0, it will be 0. Xt is equals to 0 for t less than 0. Okay. Then it is also leading to plus infinity with the ROC because it is going like this. Okay. So example problem statement we have. Let me see that. Okay. So consider we have x is equals to 1 upon s plus 2. Determine whether it's xt is right-handed or left-handed. So let me draw this. So we have, as we know, s of 2 simple it is written. How will it determine? It is left-handed or right-handed. Okay, it is right-handed. So right-handed, what was written? So as we know, s plus 2 should be greater than 0. So s should be greater than minus 2. So we have minus 2 here. Sigma 0 neighbor. This is minus 2. Greater. It is right-handed signal. For right-handed. Now for the left-handed, we have sigma 0 neighbor and minus 2 here. This is vertical strip and this is yes, this is left-handed. So s plus 2 less than 0 to s less than minus 2. So yeah, if it is greater than minus 2, as you can see here, analyze it here. You can clearly see here. But the same algebraic expressions or x of s can have different ROCs based on time domain support. So case 1, case 2. Also, as I told, what is causal and anti-causal here? So one thing to visualize, tell me which is causal and non-causal. Obviously, the first signal will be if the ROC is right-handed. Okay, then only it is causal because it is leading to plus infinity. Okay, because if you see about the left-handed signal, it is leading to minus infinity. So in that case, it is non-causal. Very, very important point to note here is, so what are the some key takeaways? Just a second. The first and foremost key takeaway is the region of interest or the region of convergence. As the name suggests, sorry, region of interest is not the one. By mistake, I told. So by as the name suggests, region of convergence, which is ROC, is very critical in determining or defining a unique inverse Laplace transform. Also, the ROC for a causal system must be the right of the rightmost pole. Why? Because we want the right one to be rightest, as you can see from this figure. If you have the right pole here somewhat, so we want this much, because as practical this much or this much, because practicality becomes from here. Okay, the more causal signal, the more practical it is. Okay, also the ROC for a causal systems must be to the right of the rightmost pole. Please remember this. This is very, 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 very important. Okay. Also, third point is the stability demands that ROC includes the imaginary axis, sigma and j. I hope this one clears to you have, suppose you have j omega this point and this is sigma. So what I'm trying to say, the stability demands this particular axis. Right now we didn't have this. So we'll see later how will we have. So practice transforms of standard functions. Illustrate partial function decomposition. Reinforce the link between the time domain signals and their transform. Let us see how we can do. So we have some more problem statements here. That is very exciting. So find the Laplace transform of x of x is xt is equals to t plus 2 e power minus 3t ut. So how will you determine this? So Laplace transform, if you say by the standard formula, so it is minus infinity to infinity x of t e power minus st ut. Again, I'm repeating here e power minus st e power minus st dt x of s. Right, right. Okay. So the standard approach to solve is also can be through this formula. Uh, but I'm removing this. Okay. So the first step is to recognize the standard transform. I will follow this path. Recognize the standard transform. Then use the linearity of the Laplace transform. Then third is use the known transform pairs where L of t a t is equals to 1 upon s minus a square, etc. We cannot follow always the formula. So rather we'll follow the steps. Let us see how. Any questions so far? So we have xt is equals to t plus 2 e power minus 3t ut. That can be written as t e power minus 3t ut plus 2 e power minus 3t ut. So Laplace transform of this is very known function, that is 1 upon s minus a square. Whereas Laplace transform of this type of function is also very known. So we will directly use it here. 1 upon s minus minus 3 is equals to s plus 3 square plus 2 into 1 upon s plus 3. We have this Laplace transform. So that was the Laplace transform, example number one. Okay. Now, simplified results, because Laplace transform won't just have the closed form equation. It should be determined what is ROC. Since the right hand side is multiplied by UT. So what is that? So yeah, by factorizing, let us factorize it here. You have S plus 3 should be equal to greater than or equal to 0 because this was the condition for stability. So this means this, and this is what ours. Okay. So what are some observation tips? So always check for the standard transform pairs to simplify calculations. Break one complex expression into sum of simpler ones, that is linearity. Keep track of ROC based on signals time domains input. First of all, first step is very, very important. Then second, then third. Okay. So let us have more complex examples. So before moving to complex examples, I hope that is clear to you. You remember Laplace transform of t power minus at ut is 1 upon s plus a square, whereas Laplace transform of e power minus at ut is 1 upon s plus a. You remember this. This is very, 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 very important. Okay. So right now we'll focus on partial fraction decomposition. We'll handle the rational function repeated rules. We will see how to invert transform symmetric systematically. So let us have the inverse Laplace transform on this. So far, so good. Just we were calculating the Laplace transform, and that was so easy. Easy piece. Okay. So for this also, what will you do? You have to first follow the inverse rules. First, what you do? You decompose into the partial decomposition. Then identify some known inverse Laplace transform and then do that. So approach will be simple, practical fraction decomposition. Second will be identify known Laplace transform. So this is first, this is second. So let us do the first thing. So we should know the formula for this. 3s plus 8. So we should be writing here like this. S plus A divided by S plus 2 plus B divided by S plus 1 plus C divided by S plus 1 square. Okay. And then equating and then solving. Because this is well known. This is well known. This is also well known formula for inverse Laplace transform. So solving, here I've given the detailed solution. Just see like this. I'm not repeating because this is just maths. Let me give some time to for you to understand this. Then give some time for the next slide. slide, you just have a calculation book. By the time, please solve by yourself. You will have the understanding. Or Tesla. Okay, so following the inverse Fourier transform here, how will I follow? This x of t is equals to Laplace inverse of x of s, and simply 2 e power minus c, because that this was the a, this was b, this was c. Okay. So each term is a standard transform pair. The presence of s power is plus 2 power corresponds to t e power minus t. Okay, that is giving me this one. So this is C, this is B, this is A. And why negative? Because B was having the value of minus 2, C is having the value of 5, and A is having the value of 2. So partial fraction decomposition is standard route for inverting rational Laplace transform. Okay. So LTI system in time domain is having this particular form. A and B power differential YT power n dtn, then differential yt, then simple linear form, and simply x of t. This is simple. And this power, this leads to s power n. S. This is s power n. This is s in Laplace transform. So replace derivatives by s multiplication. Okay, this way. Solve algebraically in s domain and use inverse Laplace transform to find y. So this is how it is done. So system analysis is the natural roots of the systems. The zeros in the frequency response. Okay, solve for this problem. So you have differential equation d2 dy t dt square plus 3 dy t dt plus 2 yt is equals to x transform. And the steps is also I have given for you. Take Laplace transform of both sides. Assuming the linear initial condition, then only it will be having the s multiplication with the power of n. Okay, solve for y of s and express the transfer function. So please have to give the closed form formula for the transfer function x of s. Waiting for just 1 minute. I'm giving to you. Oh, so sorry, my mic was muted. So I hope you all have got the expression, and this was steps. So h of s is equals to 1 upon s plus 1 into s plus 2. So what are some key observations? Suppose s minus 1 is 2. It's not stable. Both poles in the left half plane. Okay, because it is lying here and here, so all in left half only. Random solution for the step input can be formed with partial fraction inverse Laplace transform. The Laplace transforms in differential equation are in system stability. Now in the class that talks about circuit elements in the S domain. Okay, some series RLC circuit, some parallel RLC circuit, and their implications we are seeing at every aspect. So as we have the series RLC circuit, that case we have this V, this is R, this is L, this is C. Okay, so we have suppose resist that real is equals to I real. So sorry, I, so since in series we have I here. So real is nothing but R where real is equals to L dt I of s by dt. So since if it is like S domain, so how will you write? If it is an S domain, how will you write? That is L S I of S. This is simply R I of S. And VC is nothing 1 upon C, integration of 0 to t I t dt. Okay. So in that case, you can write 1 upon C as VC because integration is leading to 1 upon S. Okay. But if you talk about the just means it is leading to 1 upon CS. So and we know this can be written in terms of IC because IC the uh the the current across capacitor it's C PVC by dt. So if we only want to write in the form of T part, so that can be written, and that's why it is like this. Okay. For the Geno initial condition, this simplifies to V VL of S is equals to SLIS. AC is equals to CCV. VC. Getting so okay. Hmm. So series RLC circuit resistors will have this much in series input voltage resistor, output voltage VCT for distance. Sorry. So if we're writing the KVL in an S domain, so VI of N, the input voltage is simply V equals to. So we can write I of S is equals to V input voltage divided by R plus SL plus 1 upon SC. And voltage across capacitor is nothing but 1 upon SC. In the transfer function will get like this. So I want you to have the positive diagram, but just give me some seconds. I'll come back. I'm getting some key. So I'm coming in just 2, 3 minutes. Okay, I'm back. So we can just plot this. And for example, we have computation like this. If R is equals to 2, L is equals to 1 Henry, and C is equals to 0.5 Farad. So in that case, the poles arising from solving the equation that is now denominator, S plus 0.5 S square plus 1. And if we have to evaluate the stability damping ratio, natural frequency, we can evaluate. So the Fourier transform in complex frequency domain, we just have like this. Relate the time domain signals to their frequency domain representations. So we have complex frequency domain often uses S is equals to sigma plus j omega and links natural to Laplace transform when. Sorry. When we don't have sigma not equal to 0. So let us have some properties. Linearity, time shift, and the frequency shift and the differentiation in time domain. So there is an example problem. Find the Fourier transform if t is equals to e power minus 2t ut, where ut is in this step. You have to compute uh, f of omega provided f of t is equals to 0 for t less than 0 and f of t is equals to e power minus 2t for t greater than equal to 0. So you have to use some implications of sigma here. Just have a look at it. So basically, how will we compute this? We have a e power minus 2t, e power minus j omega. Okay. Simply 2 plus j omega. So convergence require the real of 2 plus j omega is equals to 2. Okay. That is greater than 0. So the integral converges. Okay. So what is the summary and the objectives like observations? The Fourier transform is a special case of the Laplace transform where sigma equals 0 and the poles in the complex plane determine the convergence. And this framework is crucial for understanding the frequency domain behavior of signals. So introduction to poles and zeros. The poles and zeros for which f of s is equals to infinity and zeros is f of s equals 0. These things I have already taught you. I think I have repeated here. Yeah, this is very good. Please solve the Laplace transform the ROC of the signal. I really want you to compute it and give me the closed form equation and tell me why it is anti-causal. 2 minutes. I'm waiting for you just for 2 minutes. Just let me know the closed form equation. So why this signal is anti-causal? First of all, the reason is it is defined for t less than equal to 0. Also, the ROC will lead to minus infinity, not plus infinity as we talked about. So it is going towards minus infinity, and that's why it is non-causal. And if we talk about what is a Laplace transform for that case, so it's little tricky. It's not just because as we know, this e power minus at ut has this transform formula as 1 upon s plus a. What about e power minus at u minus t? That's a good question. Okay. So simply solving here, you will have this formulation. That is uh, a different note. Okay, you have this formulation. That is very different to note. I'm just putting in the formula and keeping this value. So what I'm getting? I'm getting 1 upon x minus 3, that is denominator, multiplication with the 1 minus limit of t tends to minus infinity if e power minus t. So that is 1 minus t. So e power in infinity is what? For the limit to vanish, you should have this real of s minus 3 should be less than 0. Have you seen this anytime before? So this e power, this u of minus t, what is trying to give you? This is trying to give you the s of a that we always comes that it is greater than 0. It's not like this here. It is going to s plus a is less than 0 or whatever plus minus a. In this case here, we have s minus 3. That is simple the same formula that is s minus 1 upon s minus 3 provided s minus 3 should be less than 0. Because by putting here, you're getting this value simply for the convergence you require s minus 3 should be less than 0. In that case, real of s3 should be less than 3. So what are some confusion in the arrows? So causal signal, the ROC is the right to the rightmost pole. Anti-call is the ROC is the left to the leftmost post. Left to the leftmost pole. And the poles must lie within or on the boundary of the ROC for convergence. So let us have some basic examples over here. We will see the standard transforms like exponential sines and cosines. Focus on computing the transforms directly. So you have this as of now. Okay, just have this. What if it is e power? So in that case, the ROC will change to real of s less than the sine and cosine. You can directly calculate, but you should remember this. Why you should remember actually? Because as we know the Fourier transform, okay, that remains the Fourier transform. But when it is periodic signal, the periodic signal can be written as the sum of sines and cosines. Sum of sines and cosines. if it is periodic. If and only if it is periodic. And then in that case, you'll have the sine cosine Laplace transform. Okay. So the sine has a Laplace transform of omega naught divided by our s sine omega naught t, ka Laplace transform is omega naught divided by s squared plus omega naught squared. Whereas O of course have the Fourier transform of s divided by s plus s squared plus omega squared. Okay. So ROC is real of s should be greater than 0 for both. Why real of s is greater than 0 for both? Because denominator has squares. And that but further simplifies to somewhat s power. So in that case, real of s should be greater than not equal to also real of s should be greater than 0. That is a term. Now we'll compute some of the Laplace transform. What is the slide number? Okay. Some of the Laplace transform for the step and impulse function. So we have step function. 1 upon s, that is again unit step function, whereas del t have the Laplace transform of 1, similar to Fourier transform. The impulse function in delta t transforms to 1 for all fs, where the step function transforms to 1 upon s for real of s. So as the first and foremost difference between that is this the real and this term was not there for Fourier transform. Fourier transform we had 1 upon j omega plus some term was there, initial condition, and j omega x of 0 some was there. And here Fourier transform would have 1. So how would you do the transformations? How will you do? So first of all, memorize the most important transforms, that's exponential, sine, cosine, step, impulse that I have given you the list. Okay. They are the building blocks for almost more complex signals, but also remember for this one, t of minus at ut that was having transform of 1 upon s plus a square. Okay. Therefore, always check the ROC for each transform to ensure the validity. Let us have this advanced example overview. Then we will go directly to the questions and answers. So combination of some exponentials and polynomials, combination of piecewise defined functions, using tables and properties to speed up the calculation. So polynomial times exponential. What does the Laplace transform for that? So ft is equal to t power n e power a t ut. Then you'll have n factorial divided by s minus a n plus 1. Tell me Laplace transform is what will the Laplace transform of this one? We'll have 1 upon n factorial, sorry, n factorial was 2, so 2 divided by s minus a cube. So n factorial divided by s minus a plus 1. I'm using highlighter because that will not corrupt my notebook at the same time. And also, the real of s should be greater than a piecewise. So what is this? So you have, so this should not be highlighted. So this. I like straight curves, straight lines. That's why I think for that. This is T. This is FD. T. So this is going to be 2. So suppose we have 1. This is 2. So let's say 1. So 1 will be here. And what is 2 in that case? So 2 will be here. So 2, 2 for greater than 0, 1. Whereas 0 for this. Oh, so you have like this. So you have some discontinuity here. Okay, and this is going like this. So this what showing some sort of different implications. Decompose FT into segments and use the time shift property. Okay, let's see how will we do. Detailed solution for the piecewise function. So we can write that particular function as TUT. Okay, minus TUT minus 1 plus 2UT minus 1. How will you write? So TUT is this one. And 1 you are keeping as. So wait, how will we write? Like, let me tell you properly. I need some more space. Let me write like this. This is a simple graph, okay? So you are writing first TUT. So TUT starting from here. So it is going like this, okay? Starting from 0, this TUT. Now, minus T minus T minus TUT minus 1. So you're having suppose 1 here. So you're keeping minus. So that minus will lead to somewhat here. This is TUT. This is starting from here. This is minus TUT minus 1. Okay. And if you just sum it, it will lead to what? Will lead to 0 here, 0 or straight. Okay. Plus, you're doing plus also, plus 2. So we're having 2. Similar to what we had here, right? So whereas it is 0 here, so what? Yeah, because this is starting from 2UT minus 1. Since it is become 0, then you are adding this. And then we know TUT has this Laplace transform of 1 upon s square. And whereas Laplace transform of TUT minus 1 has e power minus s by e to the e power minus, which is it is a time shift property. Whereas okay, e power minus s for the time shift property, and this is whereas t divided by 1 upon s square. What is this? I am not sure. Yeah, so t is replaced by t plus 1. That's why it is this. And but more straightforwardly, you can write this e power Laplace transform of t ut minus 1 is equals to e power minus s Laplace transform of t plus 1 ut, and then that is giving you 1 upon s 2 of e power minus s. Final terms carefully, check for the final solution. So the TK takeaways is break down the piecewise function into simple shifted components. Use linearity and the time shifting properties. Always confirm the ROC for the each space. That's why I don't use this. I will use here a highlighter. See, highlighter will do okay here. So the concept of LTI system analysis. You have LTI system that is governed by the linear differential equation with the constant coefficients. Taking the Laplace transform simplifies solving differential equations to algebraic equations in S. And we know general differential equations have this form. Transfer function has this forms. We already talked all about this. RLC circuit, step response of the RLC circuit. You can see here for your implications, but I'm not repeating this. Anyway. The interpretation of RLC circuit also initial condition can be included or not. So we will have some of the questions and answers. Before that, if you have any questions, you can just ping me anytime. I'm waiting for any questions. And if you don't have, I will switch to the questions and answer session. Every question will be followed by detailed solution. So no worries if you don't understand it. And if you will just attend this live sessions, you'll have the understanding what type of questions will be asked in the exam. Okay. So let me proceed with the questions. So the question number one, an LTI system has a right-sided impulse response h of t. The Laplace transform ht is given by x of s is equals to -1 divided by 2s plus 1 multiplication by divided by 1 upon 2 minus 3s. Which of the following statement is true about the system? So how to solve this question? How to solve? Question number, for option number one, causal and stable. Option number two, non-causal and stable. Option number three, causal and unstable. Option number four, non-causal and unstable. So basically, you have to first see whether the poles are lying in the left half or the right half. That will give you whether the system is stable or unstable. Second thing, if it is left, right, ROC is rightmost of the rightmost pole, then it is causal. And if it is leftmost of the leftmost pole, then it is non-causal. Agree? So tick tick one, tick tick two. I'm giving you tick tick 10. If you have any answer, just tell me in the comment box. Tick tick one, tick tick two, tick tick three, tick tick four, tick tick five, tick tick six, tick tick seven, tick tick eight, tick tick nine, tick tick 10. Okay, no, so far no answer. So let me solve. How to approach this type of problem. So I have solution created for you step by step. Just have a look at it. Then I will tell you or explain. So first step is identifying the poles. So just the poles, you'll have denominator 2s plus 1, 2 minus 3s. It is giving you the pole. First pole as s is equals to 1 minus 1 by 2, and the second pole is giving us 2 plus by 3. So this pole is lying the right side. So definitely the system is not stable. Okay, right-sided causal. So for the causal system, the ROC is real of S should be greater than the rightmost pole, and the largest real pi. So you have the rightmost pole here is S equals to 2 plus 2 by 3, and the ROC would be greater than this one only. Okay, so a causal LTI system is bipole-stable if the ROC includes the imaginary axis. Okay, the ROC includes the imaginary axis. But here it is not including the imaginary axis. That is a second way to solve. This implies the system is unstable. So if ROC, if you're plotting it, it is including the ROC. But here you will have like this 2 by 3 is like here. So you'll have this. So this is not including this axis. So here it is non-stable. But obviously it is causal. So answer is causal and unstable. Conclusion, since ST is right-sided causal and the ROC must be the right of that 2 by 3, this doesn't include the imaginary axis. So system is causal and unstable. Second, an LTI system has an impulse response of h of t with a pole at s is equals to plus 5 in the Laplace domain. So which of the following statements is true? So the first option is system is definitely stable. Second option is system is definitely unstable. Third option is system can be both causal and stable. Fourth option is system cannot be causal and stable. I want answer from you guys. Tell me. How to, okay, my mic goes off. How to solve? So simply the pole is s plus 5. What does this mean? It means that pole is lying to the right height. So first of all, it is definitely unstable. So this was first point. Okay. Second is causal. So what does that mean? So causal. So it can be causal. Okay. System, if it is s plus 4, so definitely unstable. For the causality, we have to check whether the other um, other poles are there or not. So this we cannot say about now, but this is definitely unstable. So let us see the step-by-step solution. Cannot be causal. Okay, let me see how it is. So pole at S is equal to 5 lies in the right half of the hash plane. So it is unstable. Also, if the system is causal, the ROC is to the right of the rightmost pole. Okay, so if it is doesn't include the imaginary axis, that implies instability. Okay, if the system is left-handed or the anti-causal, the ROC could be less than 5, which might include the imaginary axis. In that scenario, the system could be stable but not causal. With the pole S is equals to 5, the system cannot be both stable and the causal simultaneously. Oh, yeah. So the option is simultaneously, cannot be both causal and stable. Because if it is causal, it is unstable at the same time. If it is not causal, it is stable at the same time. So the answer is C. See this step clearly. So moving to the question number 3. So the Laplace transform of sine of omega naught t ut is which of the following? And what will the ROC? My added question. So it is omega naught divided by s square plus omega naught square. That is definitely the option D. And for that, we saw that real of s should be greater than 0. That was the ROC condition. That is very, very straight. And this is a standard thing. So answer is, so see how I did. I was telling this, but by simply ignoring the steps or the options. So it is omega naught. I'm telling that it is omega naught divided by s square plus omega naught square. Still, the option I take is D. So that type of question, that type of mistakes I did even in my GATE exam. So for you not to repeat it. So answer is B. Question number 4. So the Laplace transform of delta t minus 4t is which of the following? First, e power 4t is. Second, 1 upon s e power minus 4t is. Third, e power minus 4t is or delta. Or fifth, it is delta s minus 4t. It's very, very different question and it's very good question that I have picked. So for you to understand and solve this type of problem as well. Think about it, think for some time, some seconds, then let me know. I'm telling you the deep by step-by-step solution. So let me solve. Recall the property of delta function. Uh, So if we recall the property of the delta function, so that Laplace transform of delta t minus a is equals to e power minus a of s. So by direct substitution of a is equals to 4ts, we have Laplace of delta t minus 4t is equals to e power minus 4ts. So answer is and delta shifting. Question number 5. Determine the Laplace transform for y t is equals to e power t minus 4 and xt is equals to cos t ut. Select the correct pair. Do that. Just give me some seconds and take your time. Tell me the answer. So I hope by this time you have calculated for the Laplace transform. Okay, let me give you the step-by-step solution. And for y(t) is equals to e power t minus 4, it is often implied that it is shifted as y of t is equals to e power t, starting at t is equals to 4. More precisely, if the function is t power 4 ut minus 1, then it would be like this. Simply, e power minus 4s divided by 1 upon s minus 1. Simply. But, okay, so it is often implied if t minus, it is ut minus ut also. How this is coming like this? Let me solve here. So basically t minus 4 ut minus 4. So yeah, I think I haven't written properly. It should be ut minus 4 because I have to tally with the options. So yes, so it is ut minus 4 e power minus 4s divided by 1 minus s minus 1. Why? Because e power t minus 4 is simply it's giving to e power minus 4s, but e power t is giving to 1 upon s minus 1. Okay. And for the shifting purpose, just remember like you have e power t ut, you have 1 upon s minus 1, isn't it? When you have shifted here e power t minus 4 ut minus 4, then you have shifted here e power minus 4s, 1 upon s minus 1. That's what it is written here. Simply cos t ut, you have s pi divided by s square plus 1 square because omega naught is 1 here. So omega naught 1 square is 1 only. I'm just giving this option A. I hope that you didn't stuck at that one. Okay. So also for the system defined as yt is equals to 3 e power minus 3t minus 2 e power t. Determine the region of convergence so that the system becomes unstable and non-causal. Which of the system is unstable and non-causal? So if I determine y of s is equals to 3 divided by s plus 3 minus 2 divided by s minus 1. So s plus 3 is greater than 0. So s is equals to minus 3 and s is equals to 1. So you have 1 here. So obviously the system is non, the system is, since the pole is lying this way, left side, the system is non-causal obvious now only. But you want this and this. Okay. So system is stable as of now. So system is non-causal, system is causal and stable as of now. So what do you want? So you want S, the real of S is greater than 1. So in that case, it is causal and unstable. Stable. Real of S is less than minus 3. In that case, it is non-causal and non-stable. So I think this is the answer. Definitely this not because it is involving j omega. And if it is involving j omega and ROC, that is stable. So you want unstable and non-causal. So answer is B. Oh, wait. Sorry. So let me see the step-by-step process. The term e power 3 e power minus 3t converges if real of s is greater than minus 3. If right-sided or this one left-sided. The term 2 e power minus 2 e power t converges if the real of s is greater than minus 1 left-handed or real of s is less than minus 1 right-handed, depending on how we define the signal support. To be non-causal, you would mix in left-hand sided and right-sided basis. That's why. In practice, these two exponential each want different half lengths. If they're purely right-handed, purely left-handed, there's no single RT because at some point of time you're having two exponential that they want separate half lengths. In that case, there is no single ROC that makes the entire function non-causal and non-stable in standard case. So no such ROC exists. So answer is no such ROC exists. So you have this figure. So dividing again, this is ROC1. This is ROC2. And this is ROC3. Okay. So So for ROC1, which is ROC1 here. So since it is not involving J omega, so it is unstable. And since it is like left side, so it is non-causal. So what is the answer? So non-causal, neither causal, non-stable. So answer should be D. Let me see the solution. Neither causal, non-stable. Correct only. Because it is a vertical step away from, so vertical step away from the imaginary axis doesn't include that is J omega line. This doesn't include. So non-stable stability, there's no that. For causality, ROC must be rightmost of the rightmost pole, but here the leftmost of the leftmost pole, that is anti-causal. For ROC2, let me see ROC2. This is ROC2. So blue color one. So blue color one is again the strip, but it is right side. So it is also again non-stop, non-causal, non-stable. So answer is neither causal nor stable again because it is just purely right-sided or purely left-sided. That is not the requirement. And it also doesn't include the J omega line. Question number 9. Determine which property for ROC3. So let us see ROC3 here. Since it is the rightmost side of the rightmost pole and also involving J omega, so stable and causal. It should be stable and causal. ROC3. Let me see ROC3. Causal and stable. The answer is illustrated here. So for you to repeat what are the things that you require for the causality and stability, first of all, for the causality, it should be rightmost side of the rightmost pole. So the pole was right side was the minus somewhat like this. It is -1. Okay. So -1 was this one pole. And also if it is involving J omega, that is S is equals to 0, then it is stable in that case. From ROC. But stability, what directly implies is it should have, for the bounded input, should lead to bounded output. That was the implications. Okay, that was the implication that is required. Okay, so far, if you have no doubt, then I'll end the session. And I hope you watch my recording. And if you have any doubt, you just mail me. I have told you many times. So I got mail from Manisha and some Saurav, I think. So Manisha and Saurav sent me some questions. So I think based on that questions only, I have prepared the material, because if two people are learning my recording or seeing my recording, then I have to prepare the questions according to them only. And also I'm properly making the PPTs in the proper format with proper detailed solutions. Everything is written in every PPT. So for every solution also, I'm not just telling or giving you some sort insights or like that. I'm giving you the proper solution step by step through my PPT. And first initial classes, like first 2-3 weeks, were based on the programming. Also, I added the programming notebook in that drive folder that is shared with you guys. So I hope everything is fine. So thank you so much for joining my class. Those who have joined and those who haven't missed my class, they can join. They can see my recording. That's all from my side for this week 7. Hope you to meet with week 8, week 9. So I'll tell you what are the things in week 8 and week 9 also. Let me see. See if you have any doubt, just let me know. I'm waiting. So let me share my screen to show you the content and what I have covered so far. So you can see week 7, I covered almost all the topics, frequency transform, force transform, Laplace transform, one example, two example, LTI systems, RLC circuits, all the things that was covered in the class. To week 8, we'll have Laplace transform, linear transform, shifting, and all those things we are having. Uh, but what I suggest is, if you're appearing for the exam, you should at least go through the lecture notes, if you're even if you're not watching the sessions, and some of the questions that every TAs are covering. So you'll have the proper practice that you're not missing anything. And week 2, so week 1, week 2, I think week 5 was little tough for you. That I uploaded this lecture recording very late because of some issues. But yeah, for the week 1, week 2, week till week 7, I have covered almost everything, whatever, at least the topic wise, what was there in the notes or the class. Okay. So if you have any doubt, you can have the discussion forum. I'm just telling you the discussion forum. It's there here, I think. Yeah, so for the Q&A, you have the redirected to Google discussion forum. You can discuss your queries with the course faculty as well as other students of the class. So I will suggest you to join this discussion forum. Since I am teaching this course, so I haven't joined. I have also joined as an instructor. You can mail me, but you can also join it here for further doubts. And if you say where are my recordings and all those things are there. So if you go here, problem solving sessions. So here, if you go, recording and all things are there. So you'll have this here. So if you can problem solving lectures, recordings, all this. So this is TA1, TA2, TA3. So my name is Annu, so my recordings are there. You can just let me know if you have any doubt. Presentation folder link is also there where I have uploaded everything. If you can see here. Till week 7, I think also have uploaded last yesterday. And initial week 3, if you say, I've also uploaded week 1, week 2 Python codes. Yeah, so week 2 Python codes are there that will help you to analyze things. Week 1 is also associated with the Python code. I'll suggest you to please go through this Python codes also. Okay. And yeah, so far so good. I would like to end this class, and if you have any query, just let me know because we are here to give some transformation. not just to teach or to have our basic eligibility. I want my knowledge to spread to you guys also. Okay, so now I'd like to end the class. Thank you so much for joining and see you in the next class. Okay, so I'm stopping the recording here. Thank you so much.